Will COVID-19 just go away naturally as warmer weather approaches? We shouldn't count on it. Though the common cold coronaviruses follow a seasonal pattern like the flu, peaking every winter, there are other respiratory viral infections that peak in the spring or the summer. In fact, MERS coronavirus, the last deadly coronavirus to cause an epidemic, peaked in August in the sweltering heat and blistering sun of the Arabian Peninsula. The mechanisms underlying the seasonality of viral respiratory infections remains a subject of scientific debate. It's likely a combination of factors involving the virus itself, for example, viral viability at different temperatures and humidity, host immunity, such as vitamin D status and the drying of our airways, and host behavior, like the crowding of susceptible individuals indoors. However, the near-universal susceptibility to novel pandemic viruses may supersede these seasonal factors. All the recent flu pandemics emerged in the spring or summer months, though secondary waves did tend to hit during the following winter. Even if the contagiousness of the COVID-19 virus drops this summer in the Northern Hemisphere due to warmer, wetter weather, it is not expected to make a large dent in the pandemic curve. What would stop the pandemic is herd immunity, having a critical portion of the populace immune to the virus. An infection can only burn through a population if there are enough susceptible individuals for the viral sparks to jump from one person to the next. Immune individuals who can't get or transmit the virus act as fire breaks to slow the spread, or like control rods in a nuclear reactor to break the chains of transmission. Ideally, this is accomplished through mass vaccination. Vaccines are a way to fight fire with fire, using the virus to fight the virus by generating the benefits of infection, immunity, without the risks, disease and death. Unfortunately, even though we are now developing vaccines at pandemic speed, it's humbling to realize that the average vaccine takes over 10 years to create and has a 94% chance of failure. Without a vaccine, herd immunity is only achieved the hard way, through mass infection. The proportion of the population that needs to acquire immunity to stop a pandemic can be roughly estimated from the basic reproduction number I talked about before, the number of people a single infected individual tends to go on to infect. The basic equation is p-crit equals 1 minus 1 divided by r0, where r0 is the basic reproduction number, and p-crit is what we're looking for, the minimum proportion of a population needed to be vaccinated or have recovered with subsequent immunity to smother an outbreak within that population. So if every COVID-19 case leads to 2 others becoming infected, then half of the population may need to be vaccinated or infected before the pandemic dies down. But if each person on average infects 4 others, then one would need closer to 3/4 of the population to be immune to stop it. This is an overly simplistic model, but offers a ballpark approximation. Based on R0 estimates for the COVID-19 virus from large outbreaks in affected countries, the minimum population immunity required ranges from about 30%, based on South Korea's R0 estimate of 1.43, to more like 80% based on an early R0 estimate from Spain that was closer to 5. That's why it's so important to enact curve-flattening measures like social distancing to reduce the number of contacts and drive the basic reproduction number down as low as possible. You don't want to have to wait until 80% of the population is infected. Of course, this is all working under the assumption that people who recover from COVID-19 acquire immunity to reinfection. It works in rhesus monkeys. Scientists rechallenged 2 recovered monkeys with the COVID-19 virus and were unable to successfully reinfect them. We don't yet have a definitive answer as to whether humans become immune after infection, but the fact that at least a small case series reported potential treatment benefit from convalescent plasma, the transfusion of blood products from a recovered patient, suggests the buildup of at least temporary immunity. We have 3 lines of defense against viral reinfection: circulating antibodies that can neutralize the virus, memory B cells that can create new antibodies upon re-exposure. Memory B cells are the reason people can remain immune from the chickenpox virus for 50 or more years, for example. And thirdly, memory T cells that can help hunt down virus-infected cells. The benefit of convalescent plasma derives from the antibodies, but a 6-year follow-up study of patients recovered from SARS found that about 90% no longer had any detectable anti-SARS antibodies in their bloodstreams. But that's OK, because their memory B cells could just make more, right? Unfortunately, not a single SARS-specific memory B cell was found in any of the former SARS patients. So it's definitely not something like chickenpox. Now, about 60% were able to mount a memory T cell response, though it's not clear if that alone would be able to protect them from reinfection. Unlike HIV, which keeps parts of itself hidden to evade the immune system and establish a long latent infection, the COVID-19 virus appears to take more of a smash-and-grab approach. It brazenly displays its array of spike proteins in a presumed attempt to better bind to its victim, but counts on jumping ship before immunity develops by quickly being coughed onto a new host. This bodes well for both the post-recovery acquisition of immunity and the prospects of vaccine development. A trait the COVID-19 virus does share with HIV, however, is its rapid mutation rate. One reason RNA viruses like HIV and coronaviruses and all flu viruses represent a higher pandemic threat than those that use DNA as their genetic material is that viral RNA replication can be sloppy. Every copying cycle can result in multitudes of mutants, most of which probably aren't even viable. But the flip side of this intrinsic inefficiency is that rare mutants may arise from this diverse population of variants that come exploding out of each infected cell that are either better adapted to the current host or tailored towards new ones. The high mutation rate of coronaviruses may help explain their proclivity to jump across species barriers in the first place. But the question we face now is what this new virus will do next. The genetic sequences of viral copies recovered from COVID-19 patients around the world have already diverged as much as 15% as different strains spread around the globe. Here's how rapidly the various COVID-19 strains have splayed out across the world in just a few short months. In the SARS epidemic, certain early mutants went on to dominate, which led to the supposition that genetic adaptation to humans was helping to drive the outbreak, but that remains to be substantiated. Though continued mutation of the COVID-19 virus doesn't yet offer insight into the direction of its evolution, we cannot rule out the possibility that the virus could transform to become even more transmissible or dangerous in the near future.